For the last video in this lecture series, we're going to look at how to calculate sample size and power and dive a little bit deeper into hypothesis testing than we previously have. Your clinical dilemma for this video is this. You are trying to create your first ever randomized controlled trial in what will eventually be a fruitful and engaging research career. You've developed a new medication called Research-A-Pro, which you claim turns students into extremely effective research interpreters. To test this, you develop a double-blind RCT and give half of your participants Research-A-Pro and half of the participants placebo. Both groups undergo drug literature training for 15 weeks, and then you determine which group has better course grades at the end of your study. However, you need to be careful about your sample size. On the one hand, giving an untested medication to a large group of people is an ethical concern. What if it's unsafe? What if your patients have a lot of side effects? You don't want to expose an unnecessary amount of people to those potential risks. On the other hand, you remember that small samples are more likely to be influenced by random error. If you're going to prove that your medication is truly effective and therefore reject your null hypothesis, you need to enroll enough patients to detect a meaningful difference. Sample size calculations help you weigh those two competing issues. Let's review hypothesis testing for just one moment. Remember, statistical significance testing is quantifying the probability of obtaining the observed results if there's truly no difference between groups in the larger populations from which the sample was obtained. So hypothesizing is always assuming that our random sample of participants is representative of a large population and we're not picking a biased sample. We said significance testing involves the following steps. You state the study hypothesis, formulate the null hypothesis and state your alternative, and you decide the statistical significance cutoff value, or the alpha. But at this stage, we also need to determine other significance values. The beta value is important, the sample size is important, and the power is important. Those are all decided at step 3. Then we would collect data, apply the appropriate statistical significance test, and then reject or fail to reject the null hypothesis. Earlier in the course, we looked at the alpha value and said this is the statistical significance level, but it's really the type 1 error rate, and it's always established prior to the study being conducted. There's another significance level called beta, which is the type 2 error rate. If we look at the results of hypothesis testing in our 2x2 table, we essentially see that there's the conclusion of the statistical tests and whether or not the null hypothesis was actually true. If we don't reject the null hypothesis when the null hypothesis is true, we correctly fail to reject it and there's no error. However, if the alternative hypothesis is true and we don't reject the null hypothesis, we've just made a type 2 error. This error is known as beta. It's our ability, or it's the chances that we will fail to reject the null hypothesis even though the null hypothesis was actually false. So you had positive results, but you've still failed to reject the null hypothesis. That's beta. The alpha is rejecting the null hypothesis when the null hypothesis is actually true, and alpha is deemed to be a more serious error, so alpha values are always very low, like 5%. We've discussed this previously. The other type of results, which is not an error, is correctly rejecting the null hypothesis when the alternative hypothesis is true. Let's look a little bit more at this beta value and about statistical power. So beta value is the type 2 error rate, on which we just said it's the error that occurs when the null hypothesis should be rejected but was not rejected. Beta is not always written in studies. It's more commonly expressed as power. Power is simply 1 minus the beta value. So if your type 2 error rate is 20%, then your power is 80%. Power can be broadly defined as the probability of correctly rejecting the null hypothesis if it is in fact false. In ideal scenarios, power should be 90% or higher. However, this is not always achievable because many things impact power. Things like the alpha value, the effect size, how common the outcome is in your population. Ideally, power is above 90%, but at the very minimum, it should be 80%, which means at the very maximum, your type 2 error rate should be 20%, whereas your type 1 is closer to 5%. Think of power as the ability to correctly identify a difference when a difference truly exists. If you want to look at power and how it impacts sample size, you can go onto this one website called powerandsamplesize.com. You can mess around with different study designs and see how power impacts sample size, how it's impacted by alpha, and so on and so forth. Now that we've discussed power briefly, we'll talk about sample size in a little bit more detail. Sample size is the number of patients that you need in your study to be included to have a reasonable chance of finding the statistically significant difference between groups. You can see how closely it's related to power. Having a higher sample size will give you a higher power. The more patients you have, the more ability you usually have to detect a difference between groups if one truly exists. Sample size is dependent on numerous factors. We'll talk about 4 of them, although you could argue there's up to 6 factors. The factors that we'll discuss are the type 1 error rate of the study, alpha, the type 2 error rate of the study, beta, the number of individuals in the control group who are expected to have the outcome. You can think of this as our event rate. You can also think about this as the incidence of the outcome in the control group. So note, again, that power and sample size are related, and then you need to know the difference between the groups that is likely to be considered clinically significant. So this would be the effect size. This is a table which shows the relationship of estimated sample size to some of the factors that we just discussed. For this table, you can consider the alpha value to be 5%. The leftmost column is the incidence of the outcome in the control group. The second column is the type 2 error rate, and then the 3rd through 6th columns are the outcome in the treatment group. So if we just take this first line, if the outcome in the control group is 2% and we want 10% type 2 error, meaning 90% power, and the outcome in the treatment group is 1%, that means the difference between the groups is only 1%. We need almost 4,000 patients to have that much power to detect such a small difference. However, if you go down to 20% type 2 error, you can see that reducing power allows you to have approximately 1,000 fewer patients to detect the same difference. If you went all the way up to 50% error, you would have even fewer patients required. But remember, you never ever want to have a study with more than 20% error. The 50% error is simply there to show you what would happen. If you go all the way down into the second row, say the outcome was 10% in the control group and the outcome in the treatment group is 1%, that's a 9% difference between groups. And because it's such a wide margin, this means that you need very few patients even to achieve 90% power. Take a little while to look at this table and kind of appreciate the relationships between effect size, type 2 error, and sample size, and how each can affect the other. This slide can be considered a reiteration of some of the patterns we identified on the last slide. So, sample size requirements. Some characteristics of studies that would require a very large sample size would be studies that have very small event rates because it's harder to detect rare outcomes, so we would need more patients. Studies which have smaller clinically significant effect sizes. So if we're looking at a very small difference between groups, we'd likely need a lot more patients to see that tiny difference. The smaller your effect size, the more patients you need and the lower type 2 error. If you want more power, you need more patients. The lower the error, the higher the power. Remember, these two have an inverse relationship. The opposite of the increased requirements would be decreased requirement. So if you're looking at an outcome that has a high event rate, you likely don't need as many patients because that outcome is so common. If there's a very large effect size that you're trying to find, you likely don't need that many patients to find that obvious difference between groups. Finally, if you're willing to accept a higher type 2 error, you will need fewer patients to enroll in your study. However, remember that type 2 error maxes out at 20%. And that we shouldn't be performing studies that have more than 20% error or less than 80% power. That concludes the new material for this lecture series. The next slide you should focus on to study for the quizzes and exams. First of all, you should know how to classify variables and the different classification schemes that we talked about. Know which variable is a nominal variable versus an ordinal variable versus an interval variable versus a ratio variable. So, if it's a yes-no answer, it's going to be nominal. If there's an inherent rank system to it, it's going to be ordinal if it's a discrete variable. Know the difference between interval and ratio variables. They're both continuous. Be able to calculate mean, median, and mode. Then know diagnostic test interpretation. Be able to calculate the different performance measures we talked about when you're given a 2x2 table. The equations will be provided, but also know what those performance measures inherently mean. Then for the sample size and power, know the likely effect of sample size which would occur if you change things. So if I say that the alpha value is 5%, the sample size was 150, how would it affect the sample size if I lowered the alpha value to, let's say, 2.5%? Or if I raised the effect size to be larger or smaller? How would that impact sample size? Be able to answer that type of question.